So here's the second part of the video of just energy basics, thermochemistry basics. So you learned in first year that there are processes called exothermic and endothermic processes. And if you remember, in an endothermic process, energy enters the system from the surroundings. In an exothermic process, energy leaves the system and enters the surroundings. So just to review all the ideas that you did learn from first year. So heat energy is going into the system. So the temperature of the surroundings is actually going to be decreasing because the energy is leaving the surroundings to go into the system. So the system's going to absorb the energy by increasing in kinetic energy. So it's going to get hotter. But you can't feel the kinetic energy increase. That's the thing. You can only feel the surroundings decrease. Or it's going to increase the amount of stored energy, the potential energy, which is the energy of the bond. So it's going to go into making higher energy bonds. Or the temperature, like I said, the temperature of the system is going to increase. Or it can be a combination of any of those. If the exothermic process takes place, what's going to happen? Heat's going to leave the system. So the temperature of the surroundings is going to increase. So you're going to feel the temperature get hotter because we can only feel what goes on in the surroundings. We can't feel what goes on inside the system. The energy is going to be released by the system in a couple of different ways. It's going to decrease the kinetic energy of the system. It's going to decrease the potential energy of the system, the stored molecules, the energy within the stored molecules, or it's going to decrease the temperature of the system, more likely a combination of all of the above. So once again, let's do some examples. So water being heated by the tea kettle. So focusing on the system, is water increasing or decreasing? Water is increasing in energy, so that's an endothermic system, sorry. Water is being absorbed by, or energy is being absorbed by the water. All right, the ice cube melting in the sun. Remember that the ice cube is our system. So is the ice cube increasing or decreasing in energy? It's taken energy in from the sun. So again, that's an endothermic process. The ice cube absorbs the heat and melts. And the last one, sodium fluoride is dissolved in water. That one I'm guessing you had to pause for a moment and think about because the answer is it depends. You can't make a decision without more information. You have to see what is happening to the temperature to know. Because in some cases, dissolving is an endothermic process, and in other cases, dissolving is an exothermic process. It depends upon how strong all of the different IMFAs and the ionic bonds and so on are. All right, so work in a chemical system is either mechanical or it's electrical. Electrical work is what we'll explore during the electrochem unit. That results from the movement of electrons. So we'll wait for the redox unit to take a look at that stuff. What we're going to take a look at more this now is mechanical work. So that's the result that occurs when, it could be when a gas from the reaction causes a change in volume under constant pressure. This kind of work involved is called pressure volume work. That's really the only kind, other than electrical, it's really the only kind of work. So whenever there's a gas involved where you're increasing volume or decreasing volume somehow, it's just pressure volume work that happens. And so the work, the way we define it, work is minus pressure times the change in volume, where the delta V is always the final minus initial. Okay, so here's why we're calling work negative. So the pressure is the really air pushing down on the piston compared to the reaction that's taking place inside here. So normally you're going to have a condition where the pressure is constant, but if a reaction takes place, what's going to happen? If a gas is generated, the volume is going to increase And so the work here is being done by the system. And so as the volume increases, you have negative work. If the reaction were to consume a gas where the pressure would actually decrease, then you have work being done on the system, and so then it would be a positive. So because if the system's generating if the system's generating a gas, so the volume's increasing, the system's doing the work, that's negative work, and so we want to make that a negative times a negative gives you then the positive work. All right, so enthalpy is something that we spent a lot of time in first year on. So how do we get from this energy and work and heat into enthalpy? And let's define it as well. So enthalpy is a state function used to quantify the heat flow into or out of the system. So it occurs at constant pressure. So everything on Earth that doesn't involve a gas being created or consumed or changing volume is going to simply be the energy change of the system. So we can say that the enthalpy is equal to the internal energy plus any work, any pressure volume work done by the system. So if a gas is involved, the enthalpy is more than just the internal energy. It's got to be you got to add in the work there as well. But again, we can't measure the content of enthalpy. We can only measure the change in enthalpy. So I've got to take everything and add in the change. But now I want you to remember a couple things. In previous slides, we learned that the change in energy, the change in internal energy of the system, is equal to the change in heat plus the change in work. Now we also know that delta H is equal to delta E plus P delta V. If I rearrange that equation, delta E now is also equal to delta H minus P delta V. All right, so we're going to take these two equations and do a little bit of modification and substitution. Okay, we know that work from the last slide is equal to negative P delta V. So we're going to substitute negative P delta V in here. And look what happens. Q minus P delta V, because there's W, is equal to delta H minus P delta V. Well, minus P delta V can drop out, so what are we left with? Delta H is equal to Q. So at constant pressure, the energy change of the system is equal to the enthalpy change. So this is what we worked with last year, the fact that delta H is equal to the energy change of the system. We just didn't have the work part in there. But under constant pressure, because there's no work going on, we're okay with saying this. So delta H, for all intents and purposes, is equal to the energy change of the system, or is equal to the heat change of the system. All right, so delta H is equal to the energy content of the products, the heat of the products, minus the heat of the reactants. The heat given off or absorbed, so delta H is the heat given off or absorbed during a reaction which takes place at constant pressure. So here you have a reaction that's exothermic. The reactants producing products that have less energy is an exothermic process. Vice versa, if you have a reactant having to gain energy in order to create the products, you have an endothermic process. So here, the energy of the products is less than the energy of the reactants. So delta H is smaller than 0. It's negative. Here you have the products with more energy than the reactants, and so delta H is positive, greater than 0. So for enthalpy of the reaction, we also call it the heat of the reaction. And remember that heat of the reaction is reactants minus products. Enthalpy is an extensive property. It is proportional to the quantity of material. So it matters if I use 5 grams or if I use 10 grams, I'm going to generate different quantities of overall energy. Also remember that energy changes can be reversible. The forward reaction requires energy. The reverse reaction will release the same amount of energy, but it's being released, so opposite sign. And enthalpy depends on the states of the components. So if you think about it, you know, liquid water versus gaseous water. Oh, nice. I've got arrows there that I had to take care of. Liquid water versus gaseous water versus solid water, there's different amounts of energy associated with those. So then changes in them are going to involve different amounts of energy. So if we're taking a solid to a liquid, which is an endothermic process, the system is going to absorb heat in order to do that. We're going to add energy to the system. Surroundings is going to lose it, so it's going to get, the surroundings are going to get colder. The energy's going into the system. What you see on the outside is a drop in the thermometer temperature. Why? Because the thermometer's in the surroundings. We always have the thermometer in the surroundings. We never have the thermometer in the system. So you feel it getting colder. Oh, there's where the arrow should go. Enthalpy, in this case, is going to be written as a positive because we're adding energy to the system. So in order to take solid water to liquid water, we have to add energy to the system. Delta H, like I said, is written as a positive value because it's being added. You have to add heat in order to get the reaction to work. If you're writing a thermochemical equation, remember, if you're taking this energy and putting it into the actual equation, endothermic reactions show the energy on the right as a reactant. You have to add energy to the reactants in order to get the products. In an exothermic process, obviously the opposite is going to happen. In an exothermic process, the system's giving off energy as the products are formed. So what's going to happen? The surroundings is absorbing the energy, and so the thermometer is going to rise. You're going to feel the surroundings get warmer. Where's that energy coming from? It's coming from the system. So the system is decreasing in energy, but the surroundings is gaining in energy. When you write the reaction, delta H for an exothermic reaction is always going to be written as a negative. It's the amount of energy given off, leaving, lost by. So it's not negative energy, it's just lost energy. There's a big difference. There is no such thing as negative energy. It's lost energy. And if we include the energy in a thermochemical equation, you are going to write it on the product side. Notice we're still adding it, we're just adding it to the product side. So, working with thermochemical equations, you can set up stoichiometry problems just like you can do mole problems. So, you've got the delta H for this reaction from solid to liquid being positive. If you write the reverse reaction, note that you have to make it negative. If you multiply both sides of the equation by some factor, then you also have to multiply delta H. If I'm taking 2 moles, it's going to take twice as much energy. And the physical state matters. Solid to liquid requires 6.01 kilojoules, but liquid to gas requires 44 kilojoules. And finally, a sample of how to do thermochemical equations. Hopefully you remember from first year, but if this is our equation, here's our delta H. We want to see how much heat is given off when we burn 266 grams of white phosphorus. We're going to take 266 grams, convert it into moles because that's the way the equation works, and then multiply it by, for every 1 mole of P4, we've got 3,013 kilojoules. So units cancel out. We wind up with that many kilojoules. All right, so there's the end of the video.